Hello all. Alright, so this is week 2 of our recitation. So I'm just going to get right into it. We're still talking about intermolecular forces. We're still talking about how things interact with each other. Again, inter is between molecules. When we say intra, that means between itself. So when we talk about how water is attracted to water, I'm talking about a whole molecule of water, the whole H2O molecule being attracted to another H2O molecule. And then when I talk about the intermolecular forces itself later on, we're also looking at dipole. So it's a dipole of one molecule attracted to the dipole of another molecule. So start getting that mindset. I think sometimes we overthink these things and we need to strip it down to really what that word means. So I'm going to skip over water because I feel like you guys have seen that enough. And I'm also going to skip over this dimethanethane structure. But I do want to give a hint in case you are struggling with drawing these types of things, and that carbon itself, if you know, has these four valence electrons. And so that means that there's no possible way that hydrogen is going to link together two carbons, because hydrogen itself only has one valence electron. So there's no way that can bond to two things. It can only bond to one thing and make that one bond. But carbon, on the other hand, has four. So it's more likely that these three hydrogens are going to be bonded specifically to this carbon, like so. And then it's going to bond to that neighboring C, which will again bond to two hydrogens and to the other C. So keep that in mind when you're looking at these, that carbon itself is probably what's binding a lot of these things together, only because it has four valence electrons. Same thing with oxygen. It has six valence electrons, so it has more ability to bind to more things. Just to get you into the idea of what bonds to what. Now, when I look at this methylcyanate group, I know for a fact that these two carbons are going to be bonded together. And someone's going to ask me, well, wait, but nitrogen has 5. Why isn't it nitrogen? And that's a good question. And that's only because nitrogen comes at the end here of the list. So I know that it's kind of at the end. I know that the CH3, while I know H3 is second, you're like, okay, wait, by those rules. But H3 we know can't do what we need it to do there. So we're just knowing that H3 is actually, they're going to be on the outer side. So it's going to look something like this again. And you saw how I bonded these together. And then I know the carbon, in this case, this carbon now, is going to have 4 valence electrons. One of them, of course, is now bonded to this carbon. And it has these 4 valence electrons. And I know that nitrogen as well has 5 valence electrons, right? Because we go over to our periodic table, group 15, quick cheat sheet. If it's in group 15, it probably has 5 valence electrons. Group 16, 6 valence electrons. And of course we know that since these are noble gases, they have 8 valence electrons, so they're perfectly happy. Just as a quick little side trick. Now, this is what I do. I see, okay, I can just bond this, and this. And there we go. I've officially drawn the methylcyanate group. Okay, so for intermolecular forces now, we need to figure out what's going on. And so I know that there's dispersion forces. That's going to be in everything. That's our weakest IMF. So that's everywhere. Next, I need to know about dipole. And sure enough, I do see a dipole, right? There's this carbon end side and this nitrogen end. And when I look over here, I know that nitrogen is more electronegative than carbon and way more electronegative than these hydrogens here. And so I know that there's dipole going on. There's an internal dipole plus a large internal dipole. That's kind of going to allude back here when we move on to 2. It says put the molecules in the order of increasing boiling point. Well, again, I know water is going to have the highest boiling point because that has hydrogen bonding, and hydrogen bonding is a super strong intermolecular force. It's not the strongest, so don't get confused, but it is definitely one of the stronger ones for covalent bonding, besides covalent bonds, which are very, very strong. Because remember, these are intermolecular, not intra. And so I know that water will be the biggest. It's gonna have the highest. And for those who want to know a number, 100 degrees Celsius or 212 Fahrenheit. So I know that's going to be the greatest. The next is to decide between these two. And like I said just a minute ago, we've got this dipole, which is also present here, but it's pretty weak when I think about electronegativity, because now we're saying the carbon's the electronegative one, right? Because hydrogen's not so electronegative. But the difference between them is really small. However, the difference between that carbon and that nitrogen is much larger. And so I know that the difference in that electronegativity, in the polarity of that dipole, is much greater for C. So I know that the next one in our list is going to be our methyl cyanate, and our last one is going to be that CH3CH2. Again, for the sole fact that in this case that, and I'm just going to put B, I don't want to write it all out, but because again, this has dipole-dipole, don't get me wrong, but it's a weaker dipole-dipole than this dipole-dipole. And that's all to do with electronegativity, which is going to come up in this recitation guide. So I know it's like you got to remember back, but electronegativity, we just remember fluorine's the biggest, and it dissipates down the way and dissipates across the way. Okay? Now we're going to move on. So it says draw the Lewis structures for water, carbon monoxide, and nitrogen gas, and identify the IMFs present. All right, so, and then it says water is a liquid, and explain why the other two are gases. So I'm only going to draw CO and N2. Again, we went over water in the last one, so I don't want to redo it. Just go back and watch recitation 1. So again, I'm going to draw my oxygen here. It has 6 like this, and I know that it bonds one here and one up here, which when I redraw it, then I get 2 on my carbon, and 4 left on my oxygen. There's carbon monoxide. Nitrogen's a bit easier. We get 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I know that it'll bond once and then twice. Now it's perfectly happy because that's 1, 2, 3, 4, 5, 6, 7, and 8, and then 1, 2, 3, 4, 5, 6, 7, 8. Good. So I know, or whoops, shoot. Yeah, 1, 2, 3, 4, 5, 6, 7, 8. Just so anyone who's asking, how do you know how many bonds to draw? You just want to make sure each has 8 electrons in total, and that includes sharing. Sorry, I thought the line drew and it did. So that's how they'll look. Now when I look at water, I know it has dispersion, dipole-dipole, and hydrogen bonding. When I look at carbon monoxide, I know it has dispersion, I know it has dipole-dipole, but I know it doesn't have hydrogen bonding. And then again, with nitrogen, I know it's dispersion, dipole-dipole, but it doesn't have hydrogen bonding. And so with that then lends back to why water is a liquid at room temperature, and then carbon monoxide and nitrogen gas are gases. This is because water itself has strong, attractive, cohesive forces with its hydrogen bonds. It's much more happy to be together. It has a higher surface tension. That's why in lab we always see a meniscus. And then with carbon monoxide and nitrogen gas, they themselves don't have that hydrogen bonding present. So they have weaker intermolecular forces, and that is why they are more gaseous at room temperature. All right, so draw the Lewis structure of the following. If the molecule can hydrogen bond, then draw 2 Lewis structures and identify how the molecules interact. So I'm going to skip ahead and go all the way to acetone. I think this one's a little bit trickier to see, and also a trickier Lewis structure, so I'm going to go with that one first. So again, I draw my carbons first, and I see that this one's going to bond to this carbon. It's got, again, 4. It's going to bond to this final carbon, and then it has 4 more. I know that oxygen's going to be up top here. It has these 4, and this is going to bond this way. 1, 2. So 1, 2, 3, 4, 5, 6, 7, 8. Again, 1, 2, 3, 4, 5, 6, and then 7, 8. There we go. Yep, 1, 2, 3, 4, 5, 6, 7, 8. Just showing how we count those up. I'm then going to bond these to that final valence electron on these hydrogens. All right, now hydrogen bonds can happen between 3 elements. And I'm going to tell you them while I continue drawing this structure. And that is fluorine, oxygen, and nitrogen. And I always say a funny little thing of hydrogen bonding is FON, F-O-N. And that's to say that hydrogens like to bond to a very electronegative fluorine, or the electronegative oxygen, or electronegative nitrogen. Again, when we look at our periodic table, they're all linked together, all next to each other. So these are the ones that hydrogens really like to hydrogen bond to. And that means that this oxygen up here is going to link to one of those hydrogens that's on that CH3. It can be either one, because as you can see, acetone is a mirror image, so it's symmetrical on either side. So I'm just going to show this like this onto that methyl group, and then I'm just going to draw this line and this squiggly line, which just means there's the carbonyl and the methyl group here. I just don't want to draw it all out and waste time for you. So that's how they'd hydrogen bond. All right, now rank the following bonds in order of increasing polarity. So again, we're just going to go over here and look at our electronegativity. So a carbon-carbon bond is definitely not going to be that polar. They have the same dipole moment. But then, now we're going to see carbon to fluorine. Now that's a much more bigger dipole moment. So that's going to definitely be more polar. Then I think, okay, carbon and then chlorine. So chlorine's a little less electronegative than fluorine, but still pretty electronegative. So I already know that fluorine's probably going to be number 1. So I'm going to put carbon to fluorine as my number 1, and I'm going to put carbon-carbon as my last one. And then we're between Cl and bromine here. So chlorine and bromine. Bromine is less electronegative than chlorine. And so when I think of increasing polarity between this carbon and bromine versus carbon and chlorine, I'm going to say that the carbon and chlorine is probably closer in terms of having a greater polarity. So it's closer to that fluorine than the carbon bromine. So that's how I'm going to list them. And again, it's all about that electronegativity, because that lends to the difference in that polarity, the difference in that dipole moment. Okay, moving on. Draw the Lewis structures and circle the polar molecules below. So I'm not going to draw all of these, but I am going to draw number 3, and just to give an idea of what these two will look like, and then this one I think you can lend from what 3 is drawn as. So again, I'm going to draw C. I give it 4 valence electrons. I'm going to draw chlorine on this side. I'm going to draw chlorine on this side. I'm going to draw my hydrogen. And you might ask me, well, how do you know that they're this way? And I'm going to say that, again, those H2s are together. That's Cl2 together. So they're written together. And it would otherwise mention if it were not that way. All right, so hydrogen has 1, and then chlorine has 7. So I'm just going to draw in all 7. 1, 2, 3, 4, 5, 6, 7. And I'm going to draw that bond that links all of these together. And when I see that, I can see already there is a large dipole that goes straight through here, right? This is our positive end, and this is our negative end. So when I think of what's polar, it's definitely going to be 2, 3, and 4. Now, when it says rank them, we know when we're ranking, again, we just laid back to what we talked about in 5, but now we're applying it to a whole molecule. And so when I think of increasing polarity, I'd say, okay, CBr4, which would be similar to this with bromines all around it, is definitely non-polar, because those dipoles are fighting against each other in 4 different directions there, and with that makes it non-polar. So I is definitely going to be the least polar, the least polar. And then I'm going to go here, and okay, what's going to be the most polar? Well, I'm just going to go over to my periodic table. Well, Br to Cl to F2 is in increasing electronegativity, which means an increase in that dipole. So I know that actually 2 is going to be my next in terms of kind of polar, kind of non-polar. It's going to be less polar than 3, which then I know is going to be less polar than number 4. All right? And again, it all has to do with what we talked about in 5, and again, relating that to the periodic table and relating it to your electronegativity, okay? Now, final thing, I'm just going to discuss 6 with you. You're putting 3 drops of water in a small beaker. Water likes to disperse out on that beaker. And you'll notice, though, when you use a thermometer or you've seen an old thermometer, and also if you play around with mercury, which you shouldn't be, that mercury itself beads up. And that's because mercury has a stronger, cohesive intramolecular force that keeps it together. So it's not attracted to the surface that it's on. It actually does this on a lot of surfaces. It's why cleaning up mercury is such a pain, because it'll roll around like beads. It's like dropping a bunch of marbles, except it's liquid. It's a liquid marble. It's even more annoying. And so that is because it has such a strong intramolecular force that it'll beat up on any surface and roll away, whilst water actually has a very strong attractive force. So whilst it has hydrogen bonds, that hydrogen bond really likes to be attracted to the surface. It likes the surfaces, and that's why it spreads out into a puddle. So the reason why a lot of things that are water-based will spill into a puddle. It won't necessarily just spray out flat like gas would do, but it actually has a strong enough tension to say, I want to stay with other water, but if there's already enough force to spread it out, it'll be attracted to that surface level. So we'll talk about that more in detail. If you guys have some questions, please come to my office hour if that is the case. And with that, I'm going to say thank you so much, and I will see you later.